Here we go with Chapter 14 Notes on Chemical Kinetics. To start us off, I found a really great YouTube video to talk about what different rates you might see in chemical reactions and why we care about them. I'd like you to take a few notes on your notes outline while you watch this video and note why it's important to control reaction rates and what variables might affect those rates. So here we go. Enjoy.
Engineers have a great big need to control chemical reaction speed. Fast or slow, it is to be their fate. How can we change the reaction rate? Reacting molecules do collide. Angle and energy will decide if the reaction will proceed at last, and if that reaction will be slow or fast. It's rate of reaction. Reactants form products at a certain speed. It's rate of reaction. How do we get it to serve our needs? Add or remove some steps. Make more collisions or less. Slow down or speed it on up. Some reactions happen way too fast. They can end in an explosive blast. To slow it down, you can add some steps. Use an inhibitor, then rate is less. Lower concentration or the temperature. Fewer collisions over time occur. Lower pressure if you have a gas. Less surface area for solid mass. It's rate of reaction. Reactants for products at certain speeds. It's rate of reaction. How do we get it to serve our needs? Add or remove some steps. Make more collisions or less. Slow down or speed it on up. If a reaction is too slow for you, here are a couple of things to do. Add a catalyst, some steps remove. Get that reaction running really smooth. Make more collisions happen over time. Concentration and temperature increase is fine. Raise the pressure on your gaseous friends, or crush a solid, you will meet your ends. It's rate of reaction. Reactants for products at a certain speed. It's rate of reaction. How do we get it to serve our needs? It's rate of reaction. Change the mechanism, change your steps. It's rate of reaction. How many collisions happen more or less? Change your reaction speed. Make it fit your needs. Slow down or speed it on up.
We'll talk about the video and I'll relate to it, discuss it as we go, but hopefully you got some notes about how you can speed things up or slow things down specifically. All right. This is all under the area of chemical kinetics, which is the study of the rate at which a chemical process occurs. Okay, things you heard in the video that affect reaction rates. The physical state. That's when they talked about being able to crush it. So if you need things to collide, one big chunk isn't going to work as well as powdering it up. So reactions always happen faster when you make them into smaller pieces. Concentration, as you saw in your bleach lab, higher concentration made the reaction happen faster, and you dilute it, it slows it down. Temperature, You also experience this much faster with the high temperature because, again, you're going to get more collisions. And the presence of a catalyst. We had to add the catalyst to get the bleach to break down at a reasonable rate at all. So some require it to go and some just speed up what was the reaction as it was. All right, reaction rates. How to quantify them. So the rate of a reaction is defined as the change in the concentration of either the reactants or the products as a function of time. You can choose to focus on it either way. You can see these bottles here. A represents the reactant. B, the blue, represents the product. And in the beginning, if you have all red A particles, over time, some of those are going to change into the product, and with more time, you're going to get even more of the blue and less of the red because it changes over time. The average rate is one way to describe a reaction rate, and that's change. This triangle means change in moles of B over change in time. We often look at the product because it's easier to measure oftentimes how much product is produced. Just like we did in the lab, we measured how much gas was produced rather than looking at how much bleach was used up. So change in product, amount of product over change in time. All right, suppose A forms B, and what we saw in those pictures was that at time 0, 1 mole of A, 100 represented by 100 red spheres, 20 seconds, 0.54 moles of A over 0.46 moles of B, and after 40 seconds, 0.30 moles of A and 0.70 moles of B. Every mole representing, every 0.1 mole representing one sphere. So to get an average rate, you take the change of moles over a certain amount of time. Since there was product at both 20 and 40 seconds, we can find the change between that interval. So moles of B at 20 minus moles of B at 0, or we could go 40 to 20. 0.46 over 0 for 20 seconds gives you a change in that first 20 seconds of 0.023 moles per second. How would the rate change if you were performed with respect to the disappearance of A? You can do it that way. Notice the big difference here is that you have a negative sign. So this negative sign indicates that you're losing moles of A as time progresses. And so if you did that same calculation, you can look at the moles of A over the moles of time, and you get 1.2 times 10 to the 2 molarity per second. All right, most useful units for rates look at molarity, the change of molarity. Since volume is constant, molarity and moles are directly proportional, so you can think about it either way. And in this particular reaction, we have some times and some molarities as they change over time. So this reaction is butyl chloride. But, remember, means 4 carbons. And it changes into butanol. Recognize the OH. Sorry about that. So if we look at the loss of butyl chloride, at time 0 is 0.1 molar. 50 seconds is down to 0.0905, etc., down to a 0 concentration after 10,000 seconds. So you look at average rates over, we could use time intervals of 50 seconds. So every 50 seconds, you have a certain change. In this case, it would be 0.1 minus 0.0905. That's 1.9 times 10 negative fourth molarity per seconds, because that's from 0 to 50 seconds. And notice the rate decreases as you go along. That makes sense because as there's less and less product, less and less reactants, there's fewer and fewer reactant particles, those butyl chlorides, to collide with the water to change into the alcohol. So the reaction is going to go more and more slowly over time. All right, here's the graph over several intervals of time. You've got the calculated rates of reactions at every 100 seconds in this particular graph. So those rates that we calculated would be averages because we do them over a certain time interval. If you wanted to know an instantaneous rate, that's different from the average rate because the average rates are over a certain amount of time, and even with that amount of time passing, the rates are changing. So you're going to get this curved line with the average rates changing. If you want an instantaneous rate, you draw a tangent to the graph at any particular second that you want to know the rate for. And I remember doing this in college, and you put a ruler down and you can find the slope of that instantaneous rate. There's also some calculus that can help us change from that curvy line into the straight line. And we'll get to that in a little bit later. So the average versus the instantaneous is going to depend on the goals and the questions that you're trying to answer at that particular moment. Okay, so write an expression comparing the rate of disappearance of butyl chloride to the appearance of butanol. So how would those look different from one another? Think back to a couple slides ago. If you notice, butyl chloride, because it's decreasing in amount, will have a negative sign on its calculation, and the appearance of butyl alcohol will not have a negative sign. They are equal to each other because as the butyl chloride decreases in amount, that negative sign makes it back into a positive value. And so the rate disappearance of one equals the rate of appearance of the other. By definition, you make all rates positive. Okay, sample problem. For the reaction that you just saw graphed, calculate the average rate of disappearance of butyl chloride between T0 and T100 seconds. So pause, go back and try to get the data and calculate that change. Okay, hopefully you've got that. For the rate at that, remember, this is a disappearance, so we'll have a negative value. .082 at 100 seconds minus 0.10 at 0 seconds for that data gives you a 0.0018 molarity per second rate of disappearance. All right, now sometimes you have a reaction that isn't happening at a 1-to-1 proportion. So you need to take the stoichiometry into account when you're comparing rates of one reactant to another reactant or to a different product. So for instance, if you have two hydrogen iodide molecules changing into hydrogen gas and iodide gas, you have a 2-to-1-to-1 ratio. And somehow that has to appear in your reaction, in your calculations of rate. So here's how you would do it. You take the coefficients into account by dividing them out so that all the rates are still equal mathematically. So your change in concentration of HI, missing bracket. There you go. Change in HI over change in time will be 1/2 the rate of the iodine's appearance, because you need 2 HIs for every 1 H. So if you divide this rate of disappearance by half, that should equal the rate of appearance of both iodine and hydrogen. So you take the coefficient and you divide your rate by that coefficient so that the other ones equal the same rate. To generalize, if you had an ABCD reaction, -1 over A times the rate change equals -1 over B times the rate change, which equals the appearance of 1 over C times the appearance of C rate and the appearance of D rate. Okay, another sample problem. How is the rate of disappearance of ozone related to the appearance of ozone in the following equation? So try to write yourself some rate equations for the disappearance of ozone and how it equals the appearance of O2. And then we'll calculate some values. Pause and answer that if you haven't already. Okay, so for part A, the answer would be the negative of the change in ozone concentration over 2 times the change in time equals the change in oxygen concentration over 3 times the change in time. So see how those coefficients became the divisors on the rates. So if the rate of appearance of O2, the change of O2 over change in time is 6 times 10 to the -5th molar per second at a particular instant, what is the value of the rate of the appearance of O3? So you put these numbers in here and don't forget to add the subscripts or the coefficients. Hopefully you got 4.0 times 10 to the -5th molar per second. If you had trouble with that, try it again or note that in your summary form so that we can work on that in class. All right, concentration and rate. In general, we saw in our lab that when you increase concentration, the rate is increased. If you decrease the concentration, the rate is reduced. Makes sense because more particles you have, the more collisions you have, which cause the reactions to happen. Now, to look at that in a quantitative way, let's look at the reaction between ammonium and nitrite ion to make nitrogen gas and water. Here we have a series of experiments to see how a change in concentration of one reactant affects the rate. If you notice how this is set up, in the first 3 experiments, the ammonium ion concentration was doubled each time from 1 to 2 to 0.01 to 0.02 to 0.04 molar, while the nitrite ion was kept constant at 0.2. You can see the rate change here, which must only be caused by a change in the ammonium concentration. The last 3 experiments, the ammonium was kept constant while the nitrite changed from 0.0202 to 0.0404 and again doubled to 0.0808. So any concentration change on the last 3 experiments was caused by the change in the NO2 ion concentration. So you can see, if you look closely at the data, when the ammonium was doubled, the rate doubled. 5.4 times 10 to the -7th to 10.8 times 10 to the -7th. And then if you look at 0.02 to 0.04, again, it doubled again. So it's a consistent doubling with the doubling of the ammonium concentration. When the nitrite doubles, as it does from here to here, again, you can see a doubling of the rate in both experiments. So these rates are both directly proportional to the change in concentration of the ions. That is what we call that we view a rate constant. The rate is proportional to the ammonium, it's proportional to the nitrate, and so in our case, we can make this into a rate law. So the rate equals some constant times the ammonium and the nitrite ion. And in this particular case, we could put in an understood 1 because they're directly proportional. You didn't have to square the amount of ammonium to double the rate. You just doubled it directly and the rate doubled. If you doubled this directly, the rate doubled. The K that is that proportionality constant that matches this equation is particular to any particular reaction and to any particular temperature. Okay, that rate law is important because it shows the relationship between the rate and the concentrations. In general, you'll have the same format, but there might be some exponents on the concentration to indicate what kind of change. Now those exponents, the M and the N, they tell you something called the order of a reaction with respect to each reactant. As we saw in that first ammonium and nitrite ion reaction, those M and N's would have been 1s because it was a direct proportionality between the concentration and the rate. That is called first order for ammonia and first order for nitrite, because those would have been 1s on the rate law. Now, for the overall reaction, the rate with respect to the change in both, that you would add the two together. The 1 plus the 1 gives you a second order reaction. So overall second order, first order with respect to each individual concentration. All right. So to determine the rate law, we observe the effect of initial changing conditions. We didn't talk about it, but there is a zero order reactant. And if you change that initial concentration and it doesn't have any effect on the rate, as long as some is present, well then that's called a zero order reaction. If the rate is first order, as in the one we just looked at, doubling the concentration will cause the rate to double. A second order, if doubling the concentration causes a quadruple rate. So if you substitute a 2 in for those coefficients in the rate law, and if you double a concentration, then the rate would be quadrupled, so that doubling would be raised to the second power and you would get a quadruple rate. Note that it's the rate, not the rate constant, that depends on the concentration. That K value, that constant, that stays the same no matter what happens as long as the temperature stays constant. We'll talk more about that later. So if we look at these examples here, just to use the rate law equations, this is the rate law for this reaction right here. Notice that the rate law does not obviously have a direct correlation to the reaction itself. The 2 as a coefficient on the N2O5 does not always translate into what the coefficient would be in the rate law. So you have to experimentally determine the rate law. So this is first order. First order for this one because there's an understood 1. In this reaction you have first order with respect to the CHCl3 and a half an order, so it's a 1.5 order. And this is a 1 and 1, so it's going to be a second order overall. All right, let's look over this sample problem where we look at some data to try to determine the rate law and the rate constant of the reaction. So in this we have A plus B yields C. And we have 3 different experiments where the concentrations are changed to give you different rates. So in experiment 1, 0.1 molar plus 0.1 molar gives you a certain rate. Second experiment, A has been held constant and B has been doubled. So as B is doubled, we see no change in the rate. So with respect to B, that appears to be a 0 order. B obviously needs to be there according to the reaction, but it doesn't affect the rate when you have more of it. So with A, 0.1 to 0.2, that double, we need to look at numbers 1 and 3 because B is held constant in 1 and 3 and A is doubled. So as A is doubled and B is held constant, I'm going to try another color. There we go. That'll help. The rate quadruples. Do you remember what that was from a previous slide? This is doubled and this is quadrupled. That's called a second order reaction. So when A gets times 2, if you take that time and square it, you're going to get a quadruple rate change. So at this point, we can write the rate law. So any rate of this reaction at a certain temperature equals a constant times concentration of A squared times concentration of B to the 0. All right. For B, the magnitude of the rate constant. So they're asking, okay, so what is K? If we want to find the K value, we can put in specific data from any one of the experiments. K is constant, so it shouldn't matter which one we do. So let's just do experiment number 1 to solve for B. All right, so I'm going to rearrange this. If we take the rate divided by concentration of A squared times concentration of B to the 0, we'll get K. So it's going to equal 4.0 times 10 to the negative 5th molarity per second divided by 0.100 molar squared times 100 molar raised to the 0. This cancels out because 0.100 raised to the 0, anything raised to the 0 equals 1. So if you do the math, I believe you get a K value of 4.0 times 10 to the negative 3rd. Now what units will you have here? You have molarity squared in the denominator and molarity per second in the numerator. So I believe one of the molarities is going to cancel out in the numerator and denominator. So you basically end up with seconds to the negative 1 and molarity to the negative 1. That's the unit you have left. You could write this, if you break this down into moles per liter, you'd end up with liters per second mole. Give that some thought. All right, either way is legitimate. Now, third, now that we have the K value, we can actually calculate the rate of reaction at any particular set of values at that temperature. So let's say we have A, so we want rate equals 4.0 times 10 to the negative third. And A is 0.050 molar squared. And I'm going to leave out the B part completely because it cancels out as 1. It doesn't affect the rate. So you do the math. I'm going to try the math. And I get 1 times 10 to the negative fifth molarity per second as my rate for that new set of conditions. All right, those aren't too bad. Okay, we're going to look at one more situation and then we'll call it quits for today. If our job is to convert the rate law into a convenient equation that gives us concentration as a function of time, we can look at first order as the most simple of all the reactions. Because remember, when we got that graph over time, you get a curve. And without having all the data, it makes it difficult to use in a simple way, a convenient way. So if we talk about a first order reaction, when the rate doubles, the concentration doubles. Now if you integrate that to get rid of that curve, to understand what's happening to that change, it gives you something called the natural log of the initial concentration, the concentration at any time at any time t divided by the concentration at the initial moment. So that would be the reactant that you're starting with. And that will equal the negative of the constant, the rate constant times time. This will look a little odd to you at first, but you'll get used to it. You don't need to understand where it's derived from, but I believe the book gives a nice explanation for those of you who want to know how to do that. Now, we can simplify that a little bit more into something that will be a little more familiar. Now, those of you who've worked with natural logs before, you can see here, as it's been rearranged, that if you're dividing within a natural log, that equals the natural log of the numerator minus the natural log of the denominator. And that equals negative k and t. Rearrange that, and hopefully you can see that this is a linear equation version of y equals mx plus b. So natural log of that time that you want to know the concentration for equals k as your slope, negative k, times t, plus the natural log of the initial concentration. If you have a first order reaction and you plot the natural log versus time, you get a straight line, and the slope will be negative k, and the intercept natural log of the initial concentration. So here's an example of that kind of reaction. We have methyl isonitrile changing into acetonitrile. Kind of a cool reaction because look, all that happens is the N and the C change position. So the data that you could gather directly would give you that lovely change in time, change in concentration over time, and you get a nice curved shape. When you plot that with a natural log against time, you get a straight line. That is a surefire sign that if you get a straight line with a negative slope with a natural log of the y value, that it's a first order process. Notice also that this particular rate was measured as a change in pressure, and that's perfectly acceptable. You can use molarity, but if you're studying gases, as in this particular case, pressure is more convenient and more useful in terms of keeping track. All right, you could get the slope directly from the line as one way of getting the slope, just as we got it from a series of experiments about that particular reaction. The problem for you to practice. In last year's book, this was sample exercise 14.7. Don't have a book at home, so regardless, I've got the problem here for you to try, and I'd like you to use the equation we just developed to solve for a real-world situation of a first-order reaction. So let's say we have an insecticide in the water. It decomposes. So it washes down from Mr. Smith's lawn and ends up in the lake. The water's 12 degrees Celsius, and the rate constant is 1.545 reciprocal years. This is the initial concentration when the insecticide directly goes into the water. And you assume that the lake's temperature stays the same because that's required for the constant to stay the same. So using this equation, the natural log of the concentration at time t equals negative kt plus the natural log of the concentration at time 0. I'd like you to solve for the concentration on June 1st of the following year. So when t equals 1, because the time frame is a year, solve for your A concentration at time 1 year. So put in your concentration, put in your rate constant, your time of 1, and solve for you're solving for the concentration at time t, and you're putting in the initial concentration. And for B, I want you to use the same equation, but this time you're going to solve for time, so the length of time. So solve for t. And you want your initial concentration to be the 5.0 times 10 negative 7th, and your final concentration to be 3.0 times 10 negative 7th. I'll ask you for those in your summary form, so try out those problems. See what you can do. Put those in your summary form, and I'll see you Monday. Have a great weekend. Bye, everybody.